Welcome to the sixth lecture of chapter 2. Today we're going to talk about buffers. You've heard this term probably here and there. Today we're going to put this in the context of asset base and specifically looking for how we can look at the quantity and the quality of buffers. So specifically for this lecture, we're going to understand the qualitative description of buffers, then calculate buffer intensity. So that's something very useful. And also construct graphical representation of the buffer intensity. So this lecture is very similar to the previous lecture. So we're going to use many of the content that we described in the previous lecture, and now we're approaching that from a different angle. For example, when we talk about pH-CA kind of titration diagram in the previous lecture, here we're going to twist that to talk about buffer intensity versus pH, for example. So quickly to overview what we talked about in the previous lecture, it was all about adding something that is known to an unknown, basically. So we had a titrator or a titrant, which was basically a known in terms of the composition and also the concentration. And we were adding it to the unknown. And you saw using this simple test, we were able to do to get a lot of important information from the system, like what kind of acid we might have here, both the concentration and also the pKa value. So the good thing about titration experiment, this is very simple. Basically, you just need a pipette and a known amount of acid. It's very fast. That means the operation and also reaching the equilibrium is very fast. Also, it's very informative. Two quick type of information, as I mentioned, is the total acid and also the pKa. And in terms of the graphical representation, we had the amount of acid or base added. We only cover adding strong acid or strong base. And what we were monitoring was basically the pH. And we had something like this one, in which we had, qualitatively speaking, we had regions with low change in pH and regions with high change in pH. So in this lecture, we're going to talk about more specifically about the change in pH as a function of Ca. So we're more specifically looking at what it means more quantitatively and also why we have such behavior when we add a specific acid. So this would be the focus on this lecture, basically. So more specifically about the term that we're going to describe, which is buffer. Buffer refers to how much a solution pH will change when an acid or base is added. So we kept using this resistance in the previous lecture, how much the solution is resisting against changing in pH. But here, how much pH is changing as a function of how much we're adding, we call that basically a buffer or buffer capacity. So higher the buffer capacity obviously means less change in pH when we add an acid. So when we say a solution is well buffered, that means its solution doesn't significantly change. So that's one thing. And also a poorly buffered solution, it undergoes a significant pH change when we add an acid. So in this lecture, we're going to talk about that resistance more specific. So let's describe buffer intensity. So that would be basically the whole lecture. We define this buffer intensity. The definition is pretty simple, intuitive, and that's basically the change in base or acid, and then divided by the change in pH. So very straightforward. If I'm adding a certain amount of acid to the solution, how much the pH would change. So that's basically the description of buffer intensity. Or mathematically, it means the change in Cb. Let's say if I'm adding base to the change in pH. And buffer intensity is always a positive value. So that means when you add base, the pH would increase so that dCb over dpH would be positive. If we're adding acid, we just need to apply this negative sign. So that negative means because it's always positive. So let's go back to the titration curve. Say Ca added versus pH. We had something like this. What does this mean here in the context of the figure? What is dCa over dpH, graphically speaking? Is it the slope or the inverse of the slope? Yep. So this is y, this is x, but here in this curve is basically opposite. So this is 1 over the slope of titration. So that means higher the slope, lower the buffer intensity. So here, for example, higher the slope, it means low buffer intensity, and here is high buffer intensity. So here the slope is in titration dpH over dCa, which is -1 over beta. So as we mentioned, when this is flat, the slope the slope is low. That means the buffer intensity is high, and opposite would be here. So the large slope means a low buffer intensity. And in terms of the unit, obviously it would be the representative of the unit of this one, which would be equivalent per liter or molar, as we mentioned, per pH unit. So if I'm adding 1 molar of acid, how much pH in terms of the pH unit would change? So up to this point, let's say you go to the lab, you have a titrator, or you do it manually, like adding acid, monitoring the pH. So you get this curve. Without doing any further understanding of how that beta looks like, can we construct sort of a buffer intensity kind of graph? We can, right? Because mathematically we can use sort of a programming language, converting this at each point, calculate the slope, and then pH would be our x-axis, and then the slope would be our y-axis. So we could potentially convert this into something like pH beta from here to here. But before doing that, we're going to see how we can construct mathematical description of beta value by itself without going from here to there. So before that, let's talk about something that we briefly talked about in the previous lecture, but in the context of that resistance. But here we want to talk about in the context of the buffer. So let's say I'm adding proton, like the last lecture. I'm adding proton. We are going to discuss whether this proton is consumed or is impacting the pH, exactly like what we had before. So before we show that, if I'm adding a proton, some of the proton coming from the titrant will be consumed by hydroxide to form water. So that's something that we always have. Depending on the pH, or depending on how much initially we have hydroxide, that the rate of how much I need of proton to cancel or to be involved in that reaction would change. So if we have this reaction, does it change the pH? The acid that I'm adding? It doesn't, right? So the acid that I'm adding will be consumed to form water. So it won't, you won't observe that in the change of pH if you have only this one. So no too little. So it's not just zero zeros, it's slightly, or no change in pH. What does it mean in terms of the buffer intensity? Exactly the ratio we define, or this ratio probably. Are we adding acid? So here. We're adding something, but the pH is minimal. The change in pH is minimal. What does it mean? How is this ratio? It's a very large ratio, right? So in that case, this reaction is contributing to buffer intensity. So this results in a large beta. So what it means is that we always have some buffer intensity coming from the reaction of water. So some resistance because we have hydroxide in the system, which contributes to the overall buffer intensity. So let's say if we have a weak acid. So in that case, we talked about this in the previous lecture, that some of the proton will be consumed to protonate that A minus to form the protonated version of the acid. And similarly, this has no change in pH. And similarly, this results also in large beta. So as mentioned, we are dealing with this region, so sort of a flat region. So it seems we have some contribution of the total buffer intensity related to the presence of a weak acid. So now let's say we're running out of these two, and then we add more acid. So then there's no reaction. Then whatever we add, it increases proton concentration, or it changes the pH. It results in low beta. So it seems these two have individual components or contribution to the overall buffer capacity. So now we can qualitatively describe beta to be a function of some factors related to reaction 1 and some factors related to reaction 2. So let's focus on reaction 1. If I have a sample that has a pH of 7 versus pH of 12, we have significantly more hydroxide at pH of 12. So we need significantly more of proton to be involved in this reaction before we get to the observation in pH. So it seems the buffer capacity is a function of the pH of the solution to cancel out the hydroxide. So it depends on the pH, which is related to contribution of 1. What about reaction 2? How does that impact? Can we say if we have more of a weak acid, we have more, it contributes more because you have more of A minus to protonate, right? If you have 1 millimolar of acetic acid compared to 1 molar of acetic acid, in the second case, you need to add way more Ca to neutralize it compared to the first one. So that means you need way more before the pH changes. So that means bigger buffer intensity for the second case. So this is a function of also the total concentration of acid that you have in the system. What else is missing? So let's put it this way. If we have solution A, pH 12, 1 millimolar of acetic acid, and we have we have solution 2, the same pH, the same concentration of weak acid, but this time we have ammonia. Do they have the same buffer intensity? So in the first case, when you have acetic acid at pH of 12, because pKa is 4.5, most of it is deprotonated. Most of it. As opposed to ammonia, which the pKa is 9.2. So it's less protonated. So it corrects the total, or it corrects for the concentration of the deprotonated species. So then the contribution, again, qualitatively speaking, we're going through the derivatives soon, but qualitatively speaking, the pKa is also a factor that we're expecting to see when we drive equations for beta. So we expect to see pH, which is H+. We expect to see pKa, and we expect to see also the total concentration of A, which all makes sense, right? Any other factors? Like in reality, not within the context of what we described. Any other operational factor? If we have 1 millimolar of acetic acid at pH of 12, and we run it for a temperature of 25 versus 50, do we get the same buffer intensity? Probably not, right? Because we have to correct for pKa. The pH might be impacted also. So eventually we might get that. So it could be T and other factors. But here, we just want to drive equations based on these three. Okay? So this is a qualitative description, and these two factors are related to the contribution of 2. So it seems water adds resistance. Weak acid also adds resistance or contributes to the total buffer intensity. So now we want to drive equations, how to describe buffer intensity. So let's assume we're doing titration with a strong base, which is sodium hydroxide. So that pipette we had, it's all sodium hydroxide. And now in the sample, we have water, obviously, and also we have a weak acid, let's say HA. So we mentioned that the pH of water, the total acidity, and also the pKa is all the factor that is eventually impacting how much resistance we have towards change in pH. So obviously the reaction that we're dealing with is HA, or before that even, it's always the reaction of water, and then the acid-base reaction. This is described by KW, this is KA, and also we're dealing with the total A. So now we're looking for a relationship that describes buffer intensity, that beta value, in terms of all the factors that we know about the system. So we can do, we can approach this as like sort of a speciation problem. So the species we have, as always, H plus, OH minus, A minus, HA. Anything missing? Yep. So we're adding also sodium to the system, and that would be sodium plus. So anyone can help me with the charge balance? So all the positively species plus sodium equal to OH minus plus A minus. So far we just did a charge balance and then speciation. So one factor in beta was dCB in this case to dPH. So what is CB? How we can integrate CB into this reaction, into this equation? CB is how much we added from the strong base. How we could incorporate CB here. This is what we had in the system. This is something that will be reached at equilibrium. But this is exactly how much we added. So how much of the strong base we add to the system fully dissociates. So whatever sodium we have at any point is equal to the amount of CB that was added, right? How much base we added, that means it's equal to how much concentration of sodium we have. Or at any point, if you measure the concentration of sodium, it means it's been added through addition of base. So it would be exactly equal to the base that was added. So that means the concentration of sodium is equal to CB. Again, we're driving this term. We want to use all the information to basically have an expression for beta. So CB is necessary, so we are trying to connect everything to CB. Also, we know that based on the alpha terminology, this is alpha 1 times the total of acid that was in the system initially. So this is a constant, this is a pH factor. So rearrange this means CB. So this is not, let me just change this to charge balance to avoid confusion. Now this CB, the amount of base that was added, is equal to hydroxide plus alpha 1 total minus H plus. So it seems we have an equation that has CB. So again, remember, dCB over dPH. So we have CB as a function of pH. So this is a pH dependent. This is obviously a pH factor. This is a constant, and this is also a pH dependent factor. So alpha 1 changes as a function of pH. So we have the whole expression. From here, we just need to do a little bit of a mathematical operation to get to the point to have a beta value, because the rest would be all mathematical. And you have a file uploaded on Teams. It's called differentiation rules, something like that. Just review some of the basics of how to do derivatives, for example. So you can look at it if some part of this part is confusing. But beyond this point is all mathematical. This is exactly what we need. And then the rest would be dCB over dPH. Okay? So we define beta to be dCB over dPH, or D of OH minus plus alpha 1 total A minus H plus divided by dPH. To have it a little bit more organized, we can first expand dPH, then talk about DOH minus, then this alpha term, and then eventually the H plus itself. Just to do a little bit of more organization. So the first one, we know pH is minus log of H plus. To be precise, that's activity, but here for the sake of simplicity, we just call it the concentration term, or minus 1 over 2.303 ln H plus. Just a simple conversion between log to natural log, because it's easier to work with natural log when it comes to derivatives. So now we have this expression for pH, then it would be dPH, d of minus 1 over 2.303 ln H plus. And from general mathematics, this would be minus 1 over 2.303, 1 over H plus, d of H plus. Again, if any part of this process is confusing, refer to that file. That helps you. It's just a mathematical operation from here to here. So now we know how to expand this guy to bring it in the form of dH plus. dPH was a little bit tricky to work with. We just simplified it to dH because eventually all of this are H dependent, not pH dependent, mathematically speaking. So now we can work on the second part. So the second part would be basically DOH minus over dPH. So when I say the second part, it doesn't mean this part, it means this part. And obviously the third part would be this part, and then the fourth part would be this part. So DOH minus over dPH, you have to first convert OH minus to H plus. So this would be D of KW over H plus divided by dPH, the expression we just had, 1 over 2.303, 1 over H plus, dH plus. So this is literally this one that we brought it here instead of dPH. And then we can work on this part, would be pretty straightforward. This minus KW coming out, 1 over H plus to the power of 2, D of H plus, divided by whatever we had here, 1 over H plus, DH plus. So we can now simplify this because this can be simplified a little bit more. And we get 2.303 kW over H plus, or 2.303 OH minus. So basically, this term, which contributes to beta, is equal to this part. 2.303 times the concentration of hydroxide. That's how that hydroxide that we talked about, qualitatively speaking, is contributing to the beta quantitatively. So the second part would be this guy, or the third part, third expression. So then we just need to do, again, similar expansion. Would be D alpha 1 total A dpH. And then we know what is alpha term. We can bring out total A. And then this would be D of Ka H plus Ka. So you start seeing the factors that we talked about, pH, Ka or pKa, and also the total A. So it's here and here, divided by dpH. So I'm not going to go through the derivative of this one, but eventually it would be 2.303 H plus plus Ka times Ka H plus Ka times total A. So this is basically going from here to here. It's a combination of some of the rules that we had in that review notebook. So basically this is the contribution of that weak acid on the total beta. What is this guy? What kind of alpha? This is alpha 1. So this is alpha 0. So this would be equal to 2.303 alpha 0, alpha 1, total A. So that's the contribution of weak acid on the total buffer intensity. And as we were expecting, we're seeing that Ka and also the total factors in that contribution. So the fourth one would be probably the easiest. Fourth one would be this fraction. Expand for that one. So the fourth one, it's minus dH plus over dpH, or minus dH plus over, we don't need actually parentheses. Minus dH plus over what we had, 1 over 2.303 dH plus over H plus. A little bit of simplification, 2.303 H plus. Or combining actually 2, 3, and 4, because one was basically simplifying dpH to dH. Then beta is 2.303 OH minus plus 2.303 alpha 0, alpha 1 total plus 2.303 the concentration of H plus. Or we can rearrange it a little bit. 2.303 OH minus plus H plus 2.303 alpha 0, alpha 1 total. Why do you think I rearrange it this way? What is this one? No, don't confuse yourself. What is this contribution? And what is this contribution? If you remember, we had two types of contribution on the overall buffer intensity. One was coming from the buffer intensity of water. The other one was coming from the buffer intensity of the weak acid. So this is basically the contribution of the buffer intensity of water, and this is the contribution of buffer intensity of the weak acid. So if you're given the type of acid, that means you have Ka value and you have the total concentration of the acid. At any point of pH, now you can calculate beta without having the titration curve, right? Initially, we had titration curve. We were doing this mathematical operation for point to slope and 1 minus over the slope, minus 1 over the slope. But now here we already have a mathematical or the equation as a function of pH and the features of the acid to directly calculate beta at any pH. So now we can predict that and we can construct the graph basically. So as you saw, if we have two contributions, in this case water and a weak acid, the overall is basically a combination of the two. And this was a monoprotic acid. We had one HA, and you saw the derivatives. It was all based on what HA. So if we have multiple, but monoprotic acid, then the overall contribution of HAs, so this called monoprotic, then it would be I, alpha 0 of I, alpha 1 of I, and then total A. And then this would be basically, we need the prefactors, 2.303. So if you have acetic acid, you have ammonia, you have other types of monoprotic acid, you can basically expand this one and then combine all to get the fraction or to get the contribution of all the monoprotic acid. Or in general, if you have any acid, then the contribution of all kind of acid is basically the individual contributions of acids. So this is pretty useful also, like this one specifically. If you have more than one, you can just basically have that. Any question? Okay, so we use speciation, we use charge balance. We twist it in a way that Cb shows up by connecting that to the concentration of sodium as one of the components in charge balance. Then eventually use some of the mathematical operation to get to this point to be able to calculate for the buffer intensity. So here we want to calculate for a real example. We want to estimate the buffer intensity of a solution that contains a salt of a weak acid. So basically this is 5 millimolar of ammonium chloride. And we have also a salt of another weak acid, which is sodium benzoate, which is a common food preservative. And we have a pH of 9.24, which is also the pKa of ammonia. So we know the pKa of benzoate is also 4.2. So we know for this one, we have a contribution of buffer intensity related to water, related to the ammonia system, and also related to the benzoate system. So that combining all together would be the overall contribution of beta. To a little bit expand it, so once we have ammonium chloride, it fully dissociates to ammonium plus Cl minus, and we know basically the total ammonium would be the overall we added. So total ammonium is not basically the concentration of ammonium, but it's the concentration of ammonium plus ammonia. And we know once we have ammonium, NH4, it's in equilibrium with NH3 plus H plus. Then the pKa of this one is 9.25. So that's for the first system. The second system, we have sodium benzoate. It dissociates to sodium plus, let's say, Bz minus. And then the total Bz would be 210 to the minus 3, as given. And then this Bz is in equilibrium in an acid-base reaction. HBz, Bz minus plus H plus. Then the pKa for this one is 4.20. So that's basically the equilibriums we have once we introduce ammonium chloride and sodium benzoate to the system. So the buffer intensity at the pH of 9.24 or at any pH would be the buffer intensity related to water, buffer intensity related to ammonia, and buffer intensity related to Bz, HBz. So this is basically combined together would be buffer intensity of the acid, and the first one would be buffer intensity of water. So we have concentration, we have pKa, and we have pH. So the rest would be pretty straightforward in terms of the calculation. So what is it for water? The description? Any volunteer? (2.303). Okay, OH minus plus H plus. What are the values then? So if pH is 9.24, pOH is 14 minus that. So the concentration of OH minus is 10 minus 4.76. Make sense? using this one. We have this guy, we calculate this one, and then going from POH to OH minus, which is basically 10 to the power of POH minus POH. And then the pH would be 10 to the minus 9.24. And then this would be equal to 0.04 milliequivalent per liter per unit of pH. So that's the buffer intensity contribution of water. So what is it for ammonia? Hmm? 5? So the expression was 2.03 alpha 0 alpha 1 total ammonia or 2.303 alpha 0, which is H plus plus Ka, then alpha 1, and then the total of ammonia. And we basically have all the values to insert here. Just to save some time, this would be 2.303. The pH is pKa, so then what is the alpha? Very quickly. So at pKa, we have the same amount of protonated version and deprotonated version. So this is half of the total. This is also half of the total. So alpha at pKa would be equal to 0.5. Or you can basically calculate this. So pKa is equal to pH, so these two are equal. So this one is divided by this would be 0.5 also. So whatever you prefer. But if you insert the numbers, it would be basically 0.5 for alpha 0, 0.5 for alpha 1, and then 5, 10 to the minus 3 for the concentration. Or this would be 2.88 milliequivalent per liter per unit of pH. So that's the contribution of ammonia at this pH, at this concentration, on the overall intensity of the buffer intensity. So we can do the same thing for benzoate. So beta related to, we call this HBV. Yeah. It similarly is 2.303 alpha 0, alpha 1 total BZ. Just keep in mind these values are different for HBZ and ammonia. Just keep in mind because K values are different, so these two are different. And if we do the math, this would be eventually 4 times 10 to the minus 5 milliequivalent per liter per pH. So now we can combine all together. So B, the total B or beta was the contribution of water plus the contribution of ammonia plus the contribution of benzoate would be equal to 2.92 milliequivalent per liter per pH. So now we can look at the contribution of each, the contribution of water on the overall buffer intensity. So it would be 0.04 divided by 2.92. This is roughly 1.4%. The contribution of ammonia, this would be 2.88 over 2.92. This is roughly 98.6%. And benzoate, this would be 4.10 to the minus 5 divided by 2.92. And this is basically less than 1%. So it seems they have significantly different contributions on the overall buffer intensity, mostly ammonia. So is this true for if we have the same samples, regardless of the concentration, regardless of the pH, would it be the same contribution all the time? Always 98% ammonia? What is that? So let's look back at this one. Let's assume this is like a general statement. This is a total concentration of acid. Okay, so in this case, it wasn't dramatically different, 5 millimolar versus 2 millimolar. But then alpha 0 times alpha 1, and we already know alpha 0 plus alpha 1 is equal to 1. So if you do a little bit of mathematical optimization, the maximum of the alpha 0, alpha 1 function is when we get each equal to 0.5, right? When do we get to 0.5? When the pH is equal to the pKa of that specific acid. So the reason this one has a huge contribution is because the pH was exactly equal to the pKa of ammonia. So let's say if pH was 4.20, then the contribution of HBZ would be significantly different, would be significantly higher compared to this guy. Because at that case, most of the ammonia is already deprotonated. So that could be a good actually question for the exam maybe. So we change the contribution anyway. So it seems the pKa is important, and the buffer contribution or buffer capacity for each individual acid is heavily dictated at what pH we're talking about, besides the pKa and also the total concentration. So we talked about a monoprotic acid, but as you can guess, we can also have the same derivatives for polyprotic acid, or like, for example, a diprotic acid or a triprotic acid. The same sort of procedure, charge balance, then a little bit of derivatives on different variables. Eventually, we get to these descriptions for diprotic, and this would be for monoprotic. We already proved this one. And they just simplify it from 2.303 to 0.3. So this is basically that factor of 2.303 that we had. So if you're dealing with, if you want to calculate the contribution of, let's say, carbonic acid on the buffer capacity, then you just use this variable or this expression related to the buffer capacity of the acid. If it's phosphoric acid, this is basically the one that you have to use. Again, if you have a combination of the two, let's say a diprotic acid and monoprotic acid, it would be eventually this one plus this one, because they can be combined together directly. So the derivatives also you can find it on the in the textbook, and I will not ask you to go through the same derivatives, so you don't need to go do that for, let's say, diprotic acid. But this is the expression. This table is really useful, and we will be using it later. So now we have the mathematical equation, how to calculate buffer intensity for individual species, and also the combined at each pH. So that was pretty straightforward based on the contribution of the acid and the contribution of water. So now we could do a graphical representation of the buffer intensity, as I mentioned at the beginning of the lecture. This is basically beta versus pH kind of graph. And that would be very useful to just, because again, similar to other graphical representation, it could be a quick, easy way to evaluate the system, basically. So here, the second example is asking us to construct beta pH for a monoprotic acid. We know this would be from the mathematical expression. This would be pretty straightforward. We know for pure water, beta is basically beta of H2O only, and this is 2.303 H plus plus, or H minus actually. It doesn't matter. H minus plus H plus, or 2.303 Kw over H plus plus H plus. You have the expression, and you just need to construct that spreadsheet. So you change the concentration of H plus, then you calculate obviously the pH. This would be your x-axis. Then you calculate beta, which would be your y-axis. So this is just for the case of pure water. And if you do that, this would be the blue line, the blue dashed line would be the resulting figure. Again, beta as a function of pH. So the graph is something like this one. So almost no contribution between pH of 5 to 9, no contribution on the buffer intensity, but it would contribute significantly if you go higher on either tail. So the blue dashed line is only pure water. So if we have pure water, or let's put it this way, if we have a weak acid, then beta would be beta of, let's say, HAC, and we know this would be 2.303. Alpha 0, alpha 1. The total concentration of A, or a little bit of expansion, this would be 2.303, then H plus plus Ka, and Ka H plus plus Ka, the total. So similarly, you got H plus, then pH as the x-axis. Then using this expression only, you basically calculate beta as your y-axis. And if you do that in Excel, the graph would be this one. So the green one. So as you see, the maximum buffer intensity is around 4 point something, which is exactly equal to the pKa. So the pKa is basically where you get the maximum buffer intensity. So if your pH is near that, then you get the most resistance due to that specific acid. And obviously beta of overall of the would be beta of H2O plus beta of HAC, which would be this orange line, which is literally the combination of each point. So at this point, for example, the combination of these two would be very similar to the blue one, or at this point, the combination would be this point. So we get beta of overall, this one. We get beta of the acid, and then we get beta of water. So this was the simplest case, but the procedure would be the same. So you can, regardless of what you have, how complex your system is, you can decouple them into water and the individual acids, eventually have the overall graph. And now this is the actual beta of your solution, or the resistance of your solution as a function of pH. So if you're at this point, your solution would quickly change the pH, no buffer capacity. But here, it's way more difficult because of the buffer intensity. So the next example is very similar to this one, but here, instead of a monoprotic acid, it's diprotic acid. Carbonic acid is given, the concentration we have, pKa1 and pKa2. So obviously they have two pKa's, and also the total concentration is also given. So we know beta, the total beta of beta overall, is equal to beta of water plus beta of carbonic acid. So again, this is color coded as blue, carbonic acid as green, and then this is basically orange. So similarly, we have beta H2O, the same expression, 2.303 OH minus plus H plus. But now for carbonic acid, we go back to the table basically. 2.303 alpha 0 alpha 1 plus 4 alpha 0 alpha 2 plus alpha 1 alpha 2 times the total CO3. A quick reminder, we know alpha 0 is equal to H plus to the power of 2. This is H plus to the power of 2 plus Ka1 H plus Ka1 Ka2. And alpha 1 is Ka1 H plus divided by the same denominator. And also alpha 2 would be Ka1 Ka2 divided by the same denominator. So here the process would be the same. H plus, we give H plus a value, then we calculate the pH, then we calculate beta. So this would be the x-axis, this would be the y-axis. Here, so your spreadsheet is H plus pH, alpha 0, alpha 1, and alpha 2. Then B related to water, B related to acid, and then the combined B. So, which is basically the combination of the two. So if we do for pure water, similar to the previous case, it would be something like this one. If we do only for carbonic acid, so this guy, then it would be something like this one. So as you see, it's max near the pKa. So this is pKa1 and this is pKa2. And then when we mathematically combine the two values, then this would be the orange line, so something like this one. So again, your spreadsheet goes like this: H plus, then you calculate pH, then you calculate alpha 0, alpha 1, alpha 2, then beta of H2O, beta of H2CO3, and then beta of the overall. Then you have this one and this one as a function to construct the graph. And you have the expression for each, expression for beta, expression for each individual alpha, all pH dependent. Okay, any question? So we can do also do this one for triprotic acid, like phosphoric acid, for example. One of the questions in the problem set is basically phosphoric acid. So you get, for only the acid, you get like sort of a 3 bumps, each related to 1 pKa. So as I mentioned at the beginning of the lecture, we can literally convert titration curve to buffer curve. So buffer intensity curve by taking slope for each individual point. So here, for example, what it shows is the titration of the same system, which we had ammonia in the system. And we had benzoate or benzoic acid, so BZ. So as I mentioned, the pKa for this system is 9.24. The pKa for this one is 4.20. So if we do titration, only titration on this system, then this would be the curve of titration. And in the previous lecture, we mentioned that titration curve can be used to estimate the pKa value. We find that sort of a slow slope region, like a flat region. Then we have the y values, then roughly in the middle is the pKa by evaluating that flat region. So it might be simple for like relatively simple for benzoic acid. But when we look at the ammonia, it's really hard to figure out what's the flat region and what's the extent of the flat region. Is it from here to here? Is it from here to here? Because depending on that, the value we're getting for pKa might be completely different. So we don't have like a quick visual judgment on where the pKa is. And sometimes it's really hard to get that. And this example is specifically on the ammonia side is pretty obvious. But if we calculate even the overall buffer intensity curve, then we know that this can quickly give us the values on the pKa's by looking at that sort of a peak shape. So it seems we had a peak here for benzoic acid, and then we had a peak here for ammonia. And this was, we deconvoluted basically, though this was the overall combination considering also water, because this tail is for water, this tail is for water, but these two, it seems we had two acids. And it's significantly easier to figuring out this is a pKa, and this is also a pKa. This value is 9.24, so this is 4.20. So this is a clear connection, a useful connection between the information from the titration curve and also the information from the buffer intensity curve. So if you're in the lab, you're not sure what is in your solution, by only looking at the titration curve, you might not be able to figure out the two important factors we talked about, pKa and the total acidity. But now if you mathematically even convert this one to this kind of representation, we now know that the peaks are representative of pKa. So maybe if you're developing sort of a manual for titration, you can also hypothetically talk about converting this to a buffer kind of representation to quickly, for an unknown sample, to quickly tell what kind of acid or base you might have. And this could be an interesting question for the exam. So the peaks always represent that. And this is the overall buffer intensity. If you deconvolute that, this would be something like this one. The first one, the second one, and then the third one, which is just water. Combination would be this one. So to wrap up what we talked about, we basically elaborated more on the titration curve. We mentioned that the titration curve represents a region with low or high resistance towards pH change. And this lecture, we talked about that in the context of buffer intensity. So high buffer intensity, low buffer intensity, and the schematic representation of the buffer intensity as a function of pH was basically a very useful one, because eventually we could get, let's say, a pKa value. And this was a combination of beta of water, which always exists in, of course, aqueous environment, and also the contribution of all the B of the other acids. In this case, we mostly talked about a weak acid. So eventually the curve we're getting would be a combination of all. And in the next lecture, we're going to talk about another important factor when it comes to acid-base reaction, which is alkalinity.